right, welcome to the in-class activities for week 5. We're going to go ahead and go in Blackboard, week 5 and 6. Go into reference materials. Go ahead and click on the experiment so we can read through what we're going to work through today. In week 5, we're going to work with these first sections of the programming samples. These are basic time motion, basic loop functionality, and stop at the line. Each of these are found over here in the left sidebar. So let's go ahead and click over the link for basic time motion. In class, you and your team members will read the instructions at the top of the page, work through what you should do with this program, and then you'll use the existing code, just like you did in your homework, in order to complete the challenge that's listed above. Just like we did for homework 4, go ahead and select all of the code all the way down to the bottom. Do Command C to copy and Command V to paste. Again, we can see that all of the code is present just like the code that we worked with in homework 4. Alright, so as you are working with your robot, first program is to have the robot move out and around an object. So you'll start at the start line and then make a straightaway, a left turn, straightaway, a left turn, a straightaway, and then stop, just as the diagram on your screen shows. You should work with your team to put together a flow chart to help map each step that the robot will need to take in executing this path into your MPIDE code. An example of the flowchart is shown on your screen. Alright, so just like we did for homework 4, we're going to upload this code to the robot. See what the code does before we start making any changes. Just like we worked with in homework 4, this code is designed to drive the robot forward for 1 second or 1,000 milliseconds and then to stop the robot. Let's go ahead and use this code to compute how long we need to change the delays in order to have the robot drive forward 6 inches. Alright, so we're using 4 AA batteries in the bottom of the robot to power the robot rather than using the USB cord from your computer. This is helpful because sometimes the USB cord can drag your robot and disrupt the travel of motion. So using a 1 second delay, we'll drive the robot forward for 1 second and measure how long it travels in 1 second. As the robot starts to move, we'll mark then the center axis of the wheel as how far it traveled. So here, a robot traveled about 4.5 inches in 1 second. So we'll need to use a delay of about 1,500 milliseconds or 1.5 seconds in order to get 6 inches of travel. All right, so now that you know how long of a delay you use to program the 3 straightaways for about 6 inches, you and your team will need to use an experimental trial and error process in order to calculate how long the delay should be to execute a 90-degree turn. Work with your team members on each of your 2 or 3 robots to determine what the delay is for each robot. The delays may be different from different robots. Once you've made the necessary changes to the basic time motion, your end robot travel should look something like this. You'll notice that the square isn't perfect, but it's close to what we're looking for. All right, now your team is ready to move on to the second challenge for the in-class activities in week 5. This is a basic loop functionality. Here, the goal is to have the robot drive forward for a second, stop for a second, drive forward for a second, stop for a second, repeatedly. We'll go ahead and use the code over in basic loop functionality. And as before, we'll copy all of the code and we'll paste it over here. Notice when we try to verify the code, it tells us that there are errors. And this is because we need to include the user-defined functions from the previous code. So we'll go back to the basic time motion code and scroll to the bottom. Going to catch everything that is above this green fence with the user-defined functions. And we're going to delete that code. Then we'll paste the code, some basic loop functionality, up above the user-defined functions. Now when we go to compile or verify the code, it will work. As you compare the code from basic loop functionality to the basic time motion code we worked with in the first experiment, you'll notice that the commands to move the robot forward and to stop have been moved down into the loop function rather than in the setup function. So let's upload this code to our robot and see what it does. All right, so now that we've uploaded basic loop functionality code as we've got it directly from Blackboard, let's see if this robot does what we expect it to. We're going to plug in the robot using battery power. We're hoping to see it stop and start. And as you can see, it does drive forward, but it's not demonstrating any stop. All right, you and your team will need to discuss amongst yourselves what changes you can make to the code in order to get the robot to drive forward for a second and then stop for a second. Talk within your groups about how the loop function works and what the wait time is between when the loop function goes from the closed curly brace to the open curly brace for the loop function. Refer back to the video in homework 4 if you need to. Once you've made this one-line change of code and uploaded it, your robot should perform like this. You can see the robot does stop and start even if it does not drive in a perfectly straight line. This will allow your team to finish this experiment for this challenge number 2. The final experiment that you and your group members will need to complete is stop at the line. The goal of this program is to set you and your team members up for the search and rescue, find the aluminum square in the box code that you'll work with in week 6 in your teams. In this last experiment, stop at the line experiment, you'll have your robot drive forward on the white table until it counters a black line, stop, and back up. In order to do this, you're going to need to use the light sensor as well as the servo motors to complete this exercise. So let's go ahead and take a look at Blackboard and the code that you'll need to download to complete this last experiment. Let's go ahead and pull up the stop at the line code. Just like we did with the basic loop functionality code, we're going to delete everything above the green fence in our MPIDE code and copy the code from stop at the line Blackboard down to above this fence again. So let's copy that over into MPIDE. Unlike the basic loop functionality code, here we have one more user-defined function that we need to include in our MPIDE code. This is the code that actually runs the light sensor. So we'll copy this code and then go all the way down to the very bottom, making sure that we're below this curly brace, and we'll paste that function in. Make sure that we've done everything correctly. Go ahead and verify the code and look for the message displayed in the message pane. Since it says binary sketch size, we know that this code was able to compile successfully. Before we're able to actually run this code, let's take a moment and talk through how an if statement works, because in this code, we're actually using an if statement in 2 places. And this if statement is one which we're going to work with now in class. So as in the previous flowcharts that we worked with, we'll start with a diamond for start, and then rather than stop at the bottom of the page, we'll have a return to the start of the loop function diamond as well. As in the basic time motion code, first drive forward, and then we're going to add in a new command. We're going to check the light sensor value. Your instructor and your peer mentors will be able to help you with this in class. Then we'll come to the third diamond in the flowchart. This diamond represents a decision that needs to be made in the code. Here we're going to compare the light sensor value, and if the light sensor is not less than a value that we'll calculate later, then we return back up to the drive forward square. However, if the light sensor value is, yes, less than this average value that we've selected, then the robot should stop, back up for 2 seconds, and then we'll reach the terminal diamond that will return it to the start at the top of the loop function. In order to calculate the value for the if statement in our code, we first need to measure the light sensor values over the white table and the black tape. In order to do that, we're going to use this prepared light sensor calibration code. So we'll go into Blackboard, click on that code, and then we'll select, again, everything in the code, copy it, we'll return to MPIDE, open up a new tab, and paste this code into the new MPIDE tab. Go ahead and upload this code onto our robot. Again, we may need to make sure that we've selected the correct port. We want to always use the TTY.USB serial port. Go ahead and wait for it to upload. When this bar is done, that will indicate that it has successfully uploaded. Once it's uploaded, we will use the serial monitor in order to read the values that the light sensor is collecting. Open up the serial monitor here, open up this new window, tell us what the light sensor value reading is. And just like we noticed with the stop and hold code in the homework 4, we will notice that this continues to read until we pull the plug. So let's go ahead and move over to our station to collect the values over the table and the tape. Alright, so we've got our USB cable connected to the computer and the light sensors over the white table. When you're working to collect the light sensor values, it's important that you have the USB cable connected to the computer and that you're powering the robot with the USB cable. The USB cable is what allows your light sensor to talk to the computer. With the robot placed here, I'm going to look over at my serial port, see that over the table, value is 145. Place the light sensor over the black tape, and the light sensor reading I'm seeing is 29. So now I'm going to take the average of these two values. As you can see with this function here, I'm going to add both 29 to 145 and divide by 2. The value I get out is 86. So 86 is the value that I will use in the if statement in the MPIDE code to work with the stop at the line code. Once you and your team have verified that your robot does stop at the line with the change to the if statement in your MPIDE code, next thing that you'll need to do is add 3 lines of code to have the robot back up for 1 or 2 seconds after it encounters the black line. And let me power up my robot here to show you what that should look like. And you'll test this with your team as well. See that the robot drives forward and then encounters the black line. Here you can see that the robot started to back up before it actually encountered the black line, which means that the light sensor value used in the MPIDE code was too high. So I'll go back, change that value to a number that's lower, and try again. We'll see what the robot does when it encounters the black line. You can see here that it stopped, so our value of 86 was indeed correct. We can now move on to the next part of the challenge, making the robot back up for 2 seconds after it encounters the line. It may be that for you and your team members, the black line value will be higher than 35, in which case you'll need to have one of your partners ready to catch the robot so that it doesn't drive off the table. All right, now that we've corrected the if statement, let's see if the robot behaves as we expect it to. All right, this is what we're looking for.